Hi everyone, this is Mr. Chu over here, and for this section of the video, I'm going to explain how this equation comes about. I must emphasize that this is not in syllabus. It is always good for you to know how the equation comes about, but definitely not in IB syllabus. Okay, so there are a few major ideas that I'm going to use and a little bit of math which I'm going to explain to you. Everything is on this screen. And let's start off with the basic ideas that I went through in 9.3 part 2. So I went through for two slits, two sources interference. The central maxima is where theta equals to 0. And at the first maxima, the angular position is such that sine theta is equals to lambda upon d. Now remember, when I add a third slit, I will have a secondary maxima over here like this. But what is interesting over here is that if this angular separation between the two maxima is lambda upon d, then the angular separation between here, the maxima, and its first minima, closest to it, is lambda upon 3d. So what can we gather out of this is that from the maximum to the first minima closest to it, it is the angular separation between the maximas divided by n. And remember, Rayleigh's criterion states that the two objects are just resolved when the central maxima of one source overlaps with the first minima of the other source. So that's why we need to have this position of the first minima from the other source. Now let's take a look at the separation between the two maximas of the two different wavelengths then. So the first part over here, I started off with d sine theta equals to n lambda order, which is the number of the maximas after the central maxima. Lambda, slit separation, and the angle. So I differentiated this with respect to angle theta and lambda. Why do I do that? So basically what I'm trying to find is the separation between the two wavelengths, the maxima formed by the two wavelengths, at a particular order. So that's why I want to find the resultant d theta as an effect of the difference in wavelength, two very closely packed wavelengths. So I differentiated this with respect to lambda, and I get d theta, which is the separation, the angular separation between the two maximas by the two different wavelengths of difference delta lambda. So this is due to two different wavelengths, lambda 1, lambda 2, that's the d theta. Over here, I started with the same equation, but I differentiated theta with respect to n. So what I have over here is that the lambda over here, the d theta over here, lambda upon d cos theta, is the angular separation between one wavelength, the maximas formed by one wavelength, which is like this over here. Yeah? So the angular separation between the maximas due to one wavelength. However, remember that if we have n number of slits, then the first minima beside the maxima, the angular separation, you have to divide by n. So therefore, by Rayleigh's criterion, this has to be equal to this when it is just resolved. Why? This is the angle between the two maximas, two separate maximas. So if I have one maxima forming this, I got another maxima coming in to form this. So this angular separation between the maxima is the one that we talk about over here. Now this angular separation is the angular separation between the central maxima and the first minima of the same source, the same wavelength. So when these two are equal, that's when we say that they're just resolved, and if you equate the two, you can work out this expression over here. So we developed this equation over here based on basic concepts of Rayleigh's criterion, of this observation over here, and then some simple math, we derive this expression. Alright, I hope that you have a deeper understanding why this equation is the way it is, and that you can see the basis of the equation. Thank you.